We shall quickly recall what we did in the last session. Am I right? Again, we what you call separated the variable. Am I right? We had Schrodinger equation I h bar dou psi by dou t is equal to minus h bar square by 2m dou square psi by dou x square plus v of x only psi. Am I right? We have taken what you call time independent potential situation where psi is a function of x and t both. Then we have written psi of x comma t as psi of x into phi of t, isn't it? So then we found that this psi of x is a solution of minus h bar square by 2m d square psi by dx square plus v into psi is equal to E into psi, where E is not operator, it's a what you call energy. It's a constant. Okay, so psi means psi of x. Okay, and phi of t is equal to e power minus I e t by h bar, isn't it? And our total wave function again. Now again, one more thing we found is again this one we have seen in this way: h cap into psi of x is equal to E into psi of x. Am I right? And this one also we found in a different way: E cap into psi x comma t is equal to h cap into psi x comma t, isn't it? We called this I h bar dou by dou t as E cap operator, but it's not required. Okay, it's not required. And we found a separable solution. Am I right? Psi of x comma t is equal to psi of x into phi of t. That means e power minus I e t by h bar. Since this time term comes in the e power I theta part, okay, mod psi square, everything will be independent of time, isn't it? That's why we call that in a stationary state, isn't it? And this has what you call, so again your expectation values were independent of time. Am I right? Yes. Mod psi square is also independent of time. Am I right? Mod psi square in this state. Okay, in this state mod psi square was independent of time. Any expectation values were independent of time, isn't it? So then what else? Sigma h cap is 0. Am I right? Definite energy states. Like that, we have seen the properties of this one, isn't it? Yeah. So then again we found one more thing when we solve this one. Okay, when we solve this Schrodinger time independent equation, okay, TISE, time independent Schrodinger equation. Okay, now again we may get into this one: psi 1 of x comma t is equal to psi 1 of x into e power minus I e1 t by h bar. Am I right? We get one eigenvalue, one eigenstate, isn't it? That means h cap into psi 1 is equal to e1 into psi 1. Okay, so similarly psi 2 x comma t is equal to psi 2 of x into e power minus I e2 t by h bar, and so on. Okay, then so these are all solution of same Schrodinger equation, linear differential equation. That's why linear combination is also a solution. That means most general solution is written as summation over Cn into psi n of x comma t, isn't it? Or that's equal to summation over Cn into psi n of x into e power minus I en t by h bar summation over n. Okay, just write it clearly. We call this as most general solution or linear combination of stationary state, linear combination of energy eigenstate, whatever you call, isn't it? Different name. Now in this generalized state or linear combination state, we had again, if you do energy measurement, what value you may get, isn't it? So then probability of getting En in this kind of linear combination state, we had interpretation that is equal to mod Cn square. So that means again you can once this probability is defined, so E should be normalized. Summation over mod Cn square should be equal to 1, and you can use this one to find average energy. Am I right? summation over En into probability of En. That's equal to summation over En into mod Cn square, isn't it? These are the things that we found. And also we found that, so this way of normalization, or n, I'll write summation over n. In case of a particle in a box, n will start with 1, okay? In case of harmonic oscillator, n will start with 0, okay? Yeah, so this is equal to 1. This is equivalent to normalizing this one, like this one. I think I told this one, am I right? These things. So in this kind of linear combination state, you can find h cap square also, okay? So summation over En square into probability of En, that is equal to mod Cn square, okay? So now what will happen is, using that one you can find sigma h, which may be non-zero, okay? You may have uncertainty in the measurement of energy. This is not definite energy state, okay? It is a linear combination of energy states, okay? Yeah. So let me rub out.